Last Saturday, I was supposed to be getting married. Instead, I was making videos about volcanoes. And that's because Mount Rainier, an active stratovolcano about 80 miles south of Seattle, Washington, had its largest eruption in over a decade. And as someone who studies volcanoes, I had to put my personal life on hold to talk about this very important event. But don't worry, I am now happily married. So let's talk about Rainier. Now, although Rainier put on quite the display last weekend, it's still not the most active volcano in the Cascade Volcanic Arc, which stretches roughly from southern British Columbia all the way down to northern California. That title belongs to Mount St. Helens, which blew up pretty spectacularly in 1980 and has been putting out small magma bulges and doing lots of small earthquakes ever since. But Rainier is by far the largest and also the most dangerous. The reason Rainier is so dangerous is because it's filled with so much hot, sticky magma. The magma's stickiness is why the mountain is shaped the way it is. It's called a stratovolcano, otherwise known as a layer cake volcano. These are the classic conical volcanoes that we think of when we hear the word volcano, and they get their name because they are made of layers upon layers of hardened lava flows and tephra, which is a fancy word for rock that gets blasted into the air during eruptions and can range in size from fine ash to large boulders. It's a bit like those fake foam fingers that you get at sporting events, except instead of being made of plastic, they're made of rock. Now, stratovolcanoes are what we call composite volcanoes because they're made of both hardened lava flows and pyroclastic material, which comes from explosive eruptions. In contrast, cinder cone volcanoes are much simpler. They're just piles of loose rock that have built up around a vent or a hole in the Earth's surface. They're formed by a single vent and a single eruption, and because they're only made of cinders, they tend to be much smaller than stratovolcanoes. Okay, so why does Rainier have this particular shape? It's because of the magma. See, magma, which is molten rock found beneath the Earth's surface, is created when rock deep within the planet melts due to high temperatures and pressures. But not all magma is created equal. Some magmas are very runny, while others are quite thick, and that thickness is determined by how much silica is in the magma. Silica is the main ingredient in both glass and granite, and if you've ever worked with either of those materials, you know that glass is much more runny than granite. That's because granite has more silica in it, and thus is more viscous or thick. The same thing happens with magma. Magma with lots of silica will be much thicker than magma with less silica, and the stickier the magma, the more likely it is to create explosive eruptions, and Rainier is full of really sticky magma, which is why it erupts in these little explosions every so often. This latest eruption started on May. At the time, Rainier was bulging with magma, and there had already been lots of small earthquakes in the area. Scientists had been monitoring this closely because Rainier had also been rumbling or putting out low-frequency sounds for several months prior to this. These rumblings come from gases escaping through the mountain, and when you have lots of gas trapped under a thick layer of rock, it can cause quite a lot of pressure to build up. When that pressure becomes greater than the strength of the overlying rocks, the gas will escape suddenly and explosively, and that's what happened on May. Over the course of 5 days, Rainier erupted approximately 10 times a day. The magma was blasted into the air, along with lots of steam and volcanic gases, and although the eruptions were quite spectacular, they were fairly small, reaching a height of only about 10,000 feet. Now, you might be wondering why the eruptions only reached such a small height. After all, didn't some of them reach 10 miles into the sky? Well, yes. But that's only when you measure them vertically from the summit of the volcano. In reality, they reach about 4 to 6 miles horizontally from the vent or opening of the volcano. So why isn't Rainier's magma more runny? Well, it turns out the magma is actually quite old. It's been down there for hundreds of thousands of years. And over time, the heat from the magma has baked the surrounding country rock. The country rock is basically the solid rock that the magma is pushing against. And as the country rock heated up, it released water into the magma in the form of vapor. This water has lowered the melting temperature of the magma just enough to make it more viscous. If it was more runny, it wouldn't pile up the same way. So although Rainier looks very similar to Mount Vesuvius, which famously destroyed the Roman city of Pompeii, their magmas are actually quite different. Vesuvius's magma was much more runny, and that's why it traveled much further when it erupted. In fact, Rainier's magma is so thick that even if it did flow downhill, it would only travel a few miles before hardening into a lava flow. That's good news for anyone living near Rainier, because if the magma hardens quickly, it won't be able to travel very far. However, there is another hazard associated with these explosive eruptions. Because they are so close to a densely populated area, they pose a serious risk to people living nearby, and I mean nearby. Ash and other volcanic debris rain down over a large part of Washington state, sometimes as far away as 100 miles from the volcano. And although Rainier hasn't destroyed a major city yet, it did destroy one small town. In 1792, the town of Carbonado was hit by a debris flow, or lahars, which are fast-moving mixtures of rock, soil and water that often accompany volcanic eruptions. Lahars are triggered when water mixes with pyroclastic flow deposits on the volcano's flanks. They can travel extremely far and at high speeds. And in the case of Mount Rainier, lahars have traveled as far as 25 miles from the volcano. One of the scariest things about them is that they are hard to predict. And when they occur, they are incredibly destructive. We know that lahars have occurred in the past because we can see the scars left behind on the landscape. But because they are so hard to predict, we don't know if or when the next one will happen. This is why thousands of people live within the zone of potential destruction of a lahar. So, to try and mitigate this risk, the U.S. Army Corps of Engineers constructed a series of dams around the volcano in the early 1960s. These dams were designed to catch lahars in the event they were to occur, but they're not 100% efficient. And as we saw in 1980 when Mount St. Helens erupted, some lahars can break through these barriers. And here's why we're so worried about a lahar breaking through the barriers. Although lahars are usually made mostly of rock and soil, they can carry huge amounts of water with them. In fact, a lahar that occurs during a large eruption could contain as much as 10 billion cubic feet of water. And this poses a real risk to the towns nestled at the base of Rainier. These towns sit in valleys that lahars would travel through on their way to the lowlands. So the threat is very real. And that's why there is a system in place to monitor Rainier for signs of unrest. The U.S. Geological Survey maintains a network of seismographs that surround the mountain. They use these instruments to monitor for earthquakes that may indicate magma movement. They also monitor the tilt of the mountain and even the ground beneath it. They do this by placing instruments called tilt meters on top of solid objects, such as monuments or buildings. A tilt meter is essentially a really sensitive level. And if the tilt of the ground changes, then it can indicate that the magma chamber is changing in size. They also monitor the amount of energy released by the mountain. Basically, they listen to the mountain to see if it's rumbling more than usual. All of these systems are used to try and predict when the next eruption will occur and ultimately help scientists issue warnings to the public and authorities so they can prepare accordingly. For example, if a lahar were to be detected coming down the mountain, emergency sirens would go off and residents would be told to evacuate immediately. As I said earlier, the recent activity at Rainier was not entirely unexpected. Scientists had been monitoring small earthquake swarms and increased rumbling for months prior. And in April, the United States Geological Survey issued a statement saying that the unrest may lead to an increase in eruption rates. However, no one could have predicted the timing of the eruptions or the height of the ash plume. So why wasn't there a warning for the eruption? Well, it's because we simply can't predict these things with 100% accuracy. Although Rainier had been showing signs of unrest, this did not necessarily mean it was about to blow. The increased earthquake activity and rumbling could have been caused by something else. For example, there are always small hydrothermal explosions happening on Rainier. These are explosions that occur when hot water interacts with rock and gases are released. So, although the eruption wasn't a complete surprise, it was still a surprise when it actually happened. No one knew exactly when it would take place. So should you be worried about Rainier? Probably not. As I said, the eruptions are small and they don't travel very far. In fact, the small size of the eruption is a good thing. Smaller eruptions release less gas and therefore produce less lahars. So although these eruptions may look scary, they're actually helping to reduce the chance of a catastrophic lahar occurring. Besides, Rainier is one of the most closely monitored volcanoes in the world. If there is any sign of unrest, scientists can warn the public and authorities, and hopefully everyone can stay safe. Thank you for watching this episode. If you enjoyed it, please make sure to subscribe so you never miss an exciting episode. Thanks for watching. See you next time.